So if we're looking at what limits can be found by direct substitution, first thing here that we can look at is our polynomial functions. We'll actually look at this as a property in a moment here, but polynomial functions, okay? Secondly, radical functions, except if x is approaching the end point. What did we say about x is approaching the end point? We saw an example of this on Thursday. It's not an asymptote, it's an end point here, right? What has to be true for a limit to exist? Has to be on both sides. The left and right hand limit both have to be equal. Well, if we're approaching the end point, there is no limit defined as we approach from the left because the entire function is not defined. Okay? However, any other point on that radical function, you can find the limit as x approaches that value simply by evaluating the function. Okay? Direct substitution. Alright? So, that's another case. Exponential functions. Alright? Exponential functions, we know the domain is all real numbers, right? We looked at those back in chapter 4, I believe. Okay? Exponential functions, the domain is all real numbers. There are no points of discontinuity or asymptotes in there, so we can simply evaluate that function. Okay? And really this last one here summarizes it, but it also incorporates any other type of function as long as the function is continuous around the value x is approaching. You can just evaluate the limit by direct substitution. Okay? So even if you have something like an asymptote here, okay, and then you've got, let's say you even have two asymptotes, and then you have this, this hole here as well, okay, it doesn't matter what else is going on in the function. If I'm trying to find the limit as x approaches this value, well, look around this value. We're continuous. We are approaching the same value from both sides, so I can simply evaluate, use direct substitution to get my limit. Okay? Does that make sense? Alright, as we've seen, this applies to sine curves, cosine curves, any trig function, any function at all that is continuous around the value that x is approaching. Okay? So that's just a quick summary. I'm going to give you some that you can use. You can practice this with here later. Okay? But then let's take a look at some limit theorems or properties here. Okay? First of all, the limit of a polynomial. We just said this one, but this is listed in your text as a limit theorem. The limit of a polynomial as x approaches c is simply f of c. There's our direct substitution. We're evaluating the function for x equals c. All right? Simple, easy one. The limit of a constant function. What does a constant function look like?
It's a line.
It's a horizontal line, yeah, okay? That means the value of our function is never changing. So no matter what x is approaching, the function will always equal that constant. Therefore, the limit of a constant is a constant, okay? So, those are kind of our two theorems. Now let's get into some that are a little bit more interesting. Okay? The limit of a constant multiple. This one is kind of an interesting one. let's say you have some function and then you multiply that function by 5. Okay? How would you find the limit of that new function? Well, the limit of a constant multiple of the function is the number times the limit of the original function. In other words, look, if I have the limit as x approaches c of some number b times my function f of x, if I already know the limit of f of x, okay, I already know the limit of f of x as x approaches c, then I can find the limit as x approaches c of b times f of x by simply multiplying the limit by b. Okay?
That's with any function?
Yeah, these apply to any function. Okay? So here's the deal. Let's say I had the exponential function, and I had the limit as x approaches 3 of 4 to the x. Okay? There's my exponential function 4 to the x. The limit as x approaches 3. Well, I know that 4 to the x is an exponential function. Its domain is all real numbers. So it's continuous among all real numbers. Therefore, I can simply find the limit by doing 4 to the third power and getting 64. Okay? However, let's say I want the limit as x approaches 3 of 5 times 4 to the x. Okay? According to this theorem here, what I can do is I can take this 5 and I can pull it out in front of the limit. 5 times the limit as x approaches 3 of 4 to the x. Okay? And we just found that. We know that's 64. Good. Alright, so 5 times 64 is 320. So I know the limit as x approaches 3 of 5 times 4 to the x is 320. Yes?
What if the function is like sine x?
That would work too. Okay? Let's think about it. Because that'll show up. Let's say the limit as x approaches pi over 6 of sine of x. Now you know sine of x is continuous. It's defined for the whole domain, all real numbers. So you just evaluate it. Sine of pi over 6. What's sine of pi over 6? We know this. Now pi over 6 is in the first quadrant, so we know it's positive.
It's 30, and then she's going to be 1 over 2.
1 over 2, 1/2. Good. 1/2. Sine of pi over 6 is 1/2. So now, if I wanted the limit as x approaches pi over 6, of, let's say, a 7 sine of x, I'm just going to take 7 times 1/2. Because I could pull this 7 outside of the limit. And then I just have sine of x that I'm taking the limit of. Okay? 7 times 1/2, and I get, 3.5. Alright, does that make sense? Okay? It's a really useful theorem that'll help keep your numbers small, for one thing. Smaller, and will help you evaluate things a little more efficiently. Okay? So there's another theorem, limit of a constant multiple. All right, next, the limit of a sum. Check this out. Here we have this, and we're like, oh great, a polynomial. But then we have this thing over here. Okay? if this were all we were dealing with, that goes back to our first theorem. A limit of a polynomial, we can just evaluate it, okay? And off the top of my head, I have no idea what this looks like. So is this continuous around 5? I'm not sure at first glance, okay? But the limit of a sum of different functions equals the sum of the limits of those functions. So if I want to find this, I could actually group these together. Here's a polynomial function. So I'm going to take the limit as x approaches 5 of x squared plus 3x. And then I'm going to add to that the limit as x approaches 5 of square root of x over square root of x minus 1. Okay? Now, as you get more comfortable, you may not write this out, but you're at least going to be thinking this. Okay? Yes?
Isn't there like L'Hopital's rules where you can like take the limit of the numerator and the limit of the denominator?
There is L'Hopital's rule.
I always felt the hospital.
Yeah, that's it. We're not learning that. If you go on to AP or Calc Honors, you'll learn L'Hopital's rule. Something like this, we would have to think about, okay, first of all, this is a polynomial, so I could just do 5 squared plus 3 times 5. That's done. Then we have to look at this and consider a rule. Is this continuous around 5? All right, well, what's our domain for this function right here? X cannot be 1, all right. X cannot equal 1. What else can X not be?
X greater or equal to 0.
Okay, X cannot be something that's negative, right? So X cannot be less than 0. X has to be greater than or equal to 0, and X cannot be 1. Well, if we're approaching 5, what do we know about this function then?
It's continuous at 5.
It's going to be continuous around 5, okay? The only, we've got an asymptote here at 1, and it's not even defined over to the left of 0, but around the value we're approaching, it's okay. So we can do this one by direct substitution. Square root of 5 over square root of 5 minus 1, okay? And what Justo was saying is correct. There is a rule called L'Hopital's rule where you can do it, the limit of a rational function like this, by taking the limit of the numerator over the limit of the denominator, okay? And that's essentially what we're doing. We're looking at just this function, square root of x minus 1. We're saying, okay, it's continuous around 5, and square root of x is continuous around 5, so we can do both of those by direct substitution. Okay? So, to get our answer, 25 plus 15 plus, that's 2.2 over 1.2. So that would be 11 over 6, which would be 1 5/6, about, so about a 1.83, something like that, okay? So we got 41.83, about. I'm not, again, we use our calculator, it would be a little more accurate, but you guys get the idea, okay? So, any questions about this? If you have multiple functions that you're trying to take the limit of, you can split it into separate limits. Okay? Okay, that's another theorem here. The limit of a product is the product of the limits. Okay? This is one that can definitely save you some work. We know that if you multiply this together, you would get one big polynomial function, right? But the fact is we actually don't have to FOIL here. We can evaluate this function, or this limit, by taking the limit as x approaches 5 of just the x squared plus 2 times the limit as x approaches 5 of x minus 7. Okay, you might say, well, I knew it was going to be a polynomial. Couldn't I just plug it in? Yeah. All right, but you can see the principle here and how it would apply even beyond just these polynomials. 5 squared plus 2, now we have a polynomial. 5 squared plus 2 is 27. 5 minus 7 is a negative 2, so we get a negative 54 for our limit. Again, we're trying to, a lot of what we use these theorems for, guys, is to get to things that we can then find by direct substitution. Okay, that's why we started out with that today. To look at a little more sophisticated instance of this, let's say you had the limit as x approached, let's say a pi over 2 of sine of x times tangent of x. Okay? And I have absolutely no idea what sine of x times tangent of x would look like if I were to graph it. Okay? But what I can do here is I can say, okay, well, let's break this up into two separate limits. The limit as x approaches pi over 2 of sine of x. Let's think about that one. What's the limit as x approaches 2 of sine of x? What? 1. Okay, direct substitution, that's 1. So I know it's 1 times something. What's the limit as x approaches pi over 2 of tangent of x? Is tangent continuous around pi over 2?
Undefined.
It's undefined there. Okay? This is undefined. So the limit, this limit here, does not exist. Okay?
So the answer is undefined.
So the answer is the limit does not exist. Even though the limit for the sine part of it equals something, we would say, you know, if one part of it doesn't exist, then we can say the whole thing, the limit does not exist. Okay? All right. One more here. The limit of a power. Again, this is one that can make your life much simpler, all right, because it keeps our numbers much smaller. All right, we have here the limit as x approaches some value, x of naught, of f of x to the n power is the limit to the n power. Okay, so check this out. We have this x squared minus 21 that's being cubed. And then we want to take the limit of that as x approaches 5. Well, what this theorem is saying is, hey, this is cubed. I'm going to just take the limit of what's being cubed. The limit as x approaches 5 of x squared minus 21. And then I'm just going to take my limit and cube that. Okay? Now, what's the limit as x approaches 5 of x squared minus 21? What? 4. Okay, good. 5 squared, this is a polynomial, so I'm using direct substitution. 25 minus 21 is 4. So that's the limit. And that's what I'm going to cube. 4 cubed is 64. Okay. All right. So, not too bad, right? Not too bad. The last one here actually is L'Hopital's rule that we were talking about. We just don't really use the term to keep it simple. Okay? the limit of a rational function. And it doesn't have to be necessarily a rational function as we defined it back in chapter 3 where there are two polynomials. It could be the limit of any two, of the ratio of any two functions. But there's one thing here. As long as the limit of the denominator does not equal 0, you can find the limit of the function by simply taking the limit of the top over or divided by the limit of the bottom. Okay? So as long as the limit of the denominator does not equal 0. So first of all, if we're looking at this, the limit as x approaches 3 of x plus 2. Here's our denominator. What's that going to equal?
5.
That's going to be 5. That's just a linear equation, so I can do direct substitution. It's going to be something over 5. Since that didn't come out to 0, I'll go ahead and do the numerator. The limit as x approaches 3 of x squared plus 2x minus 5. Okay? And what do we get with that?
9 plus 6.
9 plus 6 minus 5, which is 10. Good. So 10 over 5 equals 2. So this function right here is going to approach the value 2 as x is approaching 3. Okay?
Mr. Zhen,
Mm-hmm.
can you give an example that the denominator is 0?
Like this? Yeah. Okay.
It's like you knew.
It's like I knew. If we tried this one by direct substitution, square root of 36 is 6, 6 minus 6 is 0. Okay, in fact, this whole thing would be 0 over 0. Okay? And this actually won't be tomorrow, this will be in a couple days. So we'll just say later. This is what's known as an indeterminate form. You wouldn't just jump to the conclusion that, oh, it does not exist. Because actually for this one there is a limit here. But there's a little bit of a procedure that we have to follow in order to figure out what that limit is. Okay? If we wanted, we could try it on our calculators. You know, we could, with the table function, x minus 36 divided by parentheses square root of x minus 6. Okay. And I'm going to set up a table. And we want x to approach 36, right? So I'm going to have my table start at 35. And I'm going to make my delta table be a 0.1. Now we'll be able to kind of see it here, even at least with a 0.1. So if I look at my table, you see here 11.916, 11.912. We're getting closer and closer and closer. At 35.9, we're at 11.992, right? And then if we're approaching from the right, we're at 12.008. So what do you think the limit's going to end up equaling? 12. Okay, and that actually is what it ends up equaling. We've got to do some work to it, though, to get that. Okay? So, if the denominator equals 0, it doesn't necessarily mean that there is no limit. It just means that we've got to explore this problem a little further because we have this indeterminate form. Okay, and we're going to take a day or two, a couple days here, to look at those forms later. Okay? All right, so that's all the new stuff I have for you. What I want you guys to do, though, is practice, okay? So, I've got a few of these here for you to practice, 47 to 50, and then 59 to 70. All right, interpret. Make sure you identify what rule you can use, okay? And I want you to practice using the rules. Don't just do direct substitution on everything automatically. Make sure that you're considering your rules, and I want you to try to do it as efficiently as possible, okay? So, you know, try to use the rules the best you can to make your life easier, okay? If you can get comfortable using the rules rather than just, okay, well, I know I can eventually just plug it in, okay, and just blindly doing that, then, you know, it'll help you later on. The better you have these rules stuck in your head, okay? So we're gonna start looking at these.